Welcome back. In this lecture, we will discuss some simple applications of similitude to fluid mechanics. In the last lecture, we have developed some rules of thumb for similarity. We discussed that in the flow situation where with no free surface but with cavitation, that happens in badly designed pumps, siphons and torpedoes, we should match Euler number and Reynolds number. The dependence on Reynolds number is rather weak, so only the Euler number is needed to be matched in most cases. The dependence on fluid number drops out because there being no free surface. But when we have a free surface but no cavitations, like ships, dams, harbors, offshore platforms, etc., the Euler number is unimportant because there is no cavitation, so that we can take the pressure difference, which characterizes the problem as 1/2 rho V naught square, so that the Euler number drops out and only Reynolds number and fluid number are important. Again, the dependence on Reynolds number is rather low, and so we need to match fluid number. In cases when there is no free surface, no cavitation, like in submarines operating far below the surface in the deep sea, airplanes, and in closed flow in pipes, etc., we need to match only Reynolds number. Any situation where we have free surface as well as cavitation, like in high-speed ships, all the three parameters, Euler number, Reynolds number and fluid number, need to match. Let's do an example of a blimp. Blimp is a lighter than air aircraft which floats in the sky. To estimate the power requirement of a blimp traveling at 10 meters per second in air, it is proposed to test a 1/20th scale model of it in water. What should be the velocity of model in the water, and what will be the prediction rule for the power required? So that if we measure the power required for moving the model blimp in water, we can from this determine what the power required would be for the actual prototype blimp in air. Since we are working in atmosphere, we can work with gauge pressures. There is no cavitation involved. We can work with gauge pressures, and therefore we can take the characteristic pressure difference delta P naught as the dynamic pressure, the stagnation pressure, minus the static pressure, that is 1/2 rho V naught square, so that the Euler number is dropped from consideration. There is no free surface, so that we can work with non-gravitational pressure difference, and so the fluid number is also not significant. The only pi number that needs to be matched is Reynolds number. And if we match the Reynolds number, that means the value of the Reynolds number for the model is set equal to the value of Reynolds number for the prototype. This is the expression, and from this we get the velocity of the model should be 15.7 meters per second when we use 10 meters per second for VOP, that's for the prototype velocity. LOP by LOM is 20. We are using 1/20th model. We use the density of the prototype, that is density of air, divide the density of water, viscosity of water, and viscosity of air. To determine the prediction rule for power required, note that the power required is to overcome the drag. And the drag at such speeds for bodies like a blimp is dominated by pressure drag, which is the flow-wise component of pressure force integrated over the entire blimp surface. So the drag D is the integral of the gauge pressure, the component taken in the ith direction, integrated over the entire surface. Normalization of the right hand side using the characteristic gauge pressure as 1/2 rho V naught square, the dynamic pressure, and using A naught, the characteristic area, we get drag divided by 1/2 rho V naught square times A naught is equal to this integral over the entire surface. Now notice that this is in terms of the values which are normalized. When the flow over the model blimp is the same as flow over the prototype blimp, the values of the normalized variables is identical. That is the consequence of similarity. And so this integral would be the same in prototype as well as in the model. That means this value, which incidentally is defined as a drag coefficient, is the same in the prototype and in the model. So drag of prototype or drag of model should be equal to 1/2 rho V naught square dot AP for the prototype divided by the same for the model. And the work done would be drag times the velocity. And using this expression, we get this, or that the ratio of the power requirement for the prototype divided by power requirement for the model is 0.125. So the prototype uses only 1/8 power of the power used by model. The model would use 8 times the power of the prototype. Why is this so? This is largely because the model is moving in water, and the water is lot denser, almost 1,000 times denser, and therefore you'll need to do a lot of work and spend a lot of power in moving the blimp at a similar speed. Let's do another example, an example where cavitation is involved. Cavitation on torpedo fins. Torpedoes, when they move at very high speeds, and on the fins, the velocity is very large, and so cavitation occurs. This cavitation is quite harmful when the pressure increases on the vapor bubble, that is, when the liquid speed decreases, the bubble collapses in the manner shown, and there is a kind of a water jet impinges on the nearby surfaces. This causes surface erosion. This picture denotes the cavitation damage done on the impeller of a water pump. I couldn't find an image of a damage done to the torpedo fence, but the damage is quite serious, and this is an example of the damage done. The problem that we have is that a torpedo of diameter 20 centimeter is seen to be on the verge of cavitation at a speed of 30 meters per second when running 10 meters below the ocean surface. The ocean is at temperature of 20 degrees Celsius. Why do we need to specify the temperature? Because cavitation is occurring. And so the vapor pressure is important. And the vapor pressure depends very strongly on the temperature. So we need to know the vapor pressure of water at 20 degrees Celsius. Now the problem is to determine at what speed must the torpedo run if it is traveling at 50 meters per second. It is traveling that fast, so the pressure drop would be larger. And since the cavitation pressure is the same, the temperature is 20 degrees Celsius, then it means the ambient pressure must be larger. And that would mean that the torpedo, if it is to avoid cavitation, must run much deeper than 10 meters below the ocean surface. Let's determine that. As 10 meters is fairly large compared to the torpedo size of 20 centimeters, the fluid number does not need to be matched. We can ignore the free surface of the water. And when we can replace the pressure by the non-gravitational pressures given by P script as P plus rho gz minus P naught. But since the cavitation is involved, the Euler number is now to be matched. And the Euler number must be defined with P naught minus PV taken as the characteristic modified pressure difference. That is, these two values, one for the prototype and the other for the model, must match. The value of script P minus script PV is P plus rho gz minus P naught reference, which could be at the level, at the surface of the sea, minus P plus rho gz minus P naught when the cavitation occurs. Taking the datum at the ocean surface where P is P naught and Z is equal to 0, we determine the value of P naught minus PV script as P naught minus PV minus rho gz. For the model, this value is determined to be 200 kilopascal. When you plug in all the given values, the equivalence of the Euler number between the model and the prototype then gives the value of P naught minus PV for the prototype as 555.7 kilopascal. Almost 2.5 times that for the first case. And from this we can determine the depth must be 45.2 meters. So if the torpedo has to operate at a much larger speed, then it must move deeper. So 10 meters, 45.2 meters to avoid cavitation. I hope this example clarifies the use of modeling rules in cases where cavitation is involved. Cavitation is not always damaging. In the late 1940s, Soviet scientists began to wonder if by deliberately manipulating cavitation effects to create a large, huge, sustainable mega bubble that encases the torpedo body within it, hydrodynamic drag could be largely overcome. So that if we can create a cavitation bubble such that the whole body of the torpedo is enclosed within this as shown here, then this is all vapor. So the drag on the torpedo would be greatly reduced. After 2 decades of work and 6 prototypes later, practical super-cavitation was realized, and the work saw the emergence of a new weapon class capable of remarkable submerged speeds. Since the drag is much lower, the speeds can be much larger. Cavitation, instead of going against us, is now helping us. Now let's do a little more complicated problem. This is a problem which is known as Rayleigh-Stokes flow, or the Stokes' second problem in fluid mechanics. The problem situation is simple. We have a flat plate which is oscillating in a liquid which was initially quiescent, not moving at all, and this plate is vibrating at a speed which is given by V0 sine omega t. That is, with an amplitude V0 and a circular frequency omega. Because of the no-slip condition, the fluid adjacent to the plate starts moving, and as it moves, it causes shear stress on the rest of the fluid, and the effect of the movement of the plate penetrates upward. But soon the direction of motion changes, so everything reverses. And because of this, at any given time, the effect of the motion of the plate does not penetrate to more than a fixed distance. We have to determine what is the extent of the region of fluid near the plate that is affected by the motion of the plate. We start with the governing equation. This is the equation of motion of the fluid when there is only one component of velocity u and there is no pressure gradient in x, y, or z direction. And so the equation of motion simplifies to this. Rho del u by del t is equal to mu del square u by del z square. This unsteady flow with only one component of velocity, which is a function only of z and of course t. This partial differential equation is not very difficult to solve. It has to be solved with the no-slip condition at the plate, which would say that the velocity u would be equal to the velocity of the plate at any given instant, V0 sine omega t. And far away, the velocity would be 0 for all times. We define the normalized velocity u star as u divided by V0, the amplitude of the velocity of the plate, and we define t star as omega t, 1 omega is the characteristic time. So omega t becomes a non-dimensionalized normalized time. And we define a normalized z variable z star as z divided by L naught, where L naught is some characteristic length in the z direction. What is that characteristic length? We don't know. In fact, this is where half the story is. So L naught is as yet unknown. If we do the transformation, the normalized equation looks like this. With the boundary condition that u star is equal to sine t star on z star is equal to 0, and u star at infinity for all times is 0. They're far away boundary conditions. And so u star now is a function of two independent normalized variables, z star, t star, and one parameter nu divided by omega L naught square. Now comes the interesting part. This is an unsteady flow problem, and there is a viscous flow. Viscosity is central to the problem. We cannot neglect viscosity. So both terms in this equation must be retained. None of the terms must drop out. Since this derivative of normalized variable and this derivative of normalized variable by definition are order 1 normalized, and so this coefficient must be of order 1. And this gives you a definition of L naught. Because if this is of order 1, then L naught must be equal to nu divided by 2 omega. If we use this, L naught should be of order nu divided by twice omega. We can set it equal to this. So L naught is equal to nu divided by twice omega. This graph shows the variations of the velocity profile with time for 3 different cases of omega. This is for the fastest omega, this curve which goes only up to about this height. There are 3 curves. One of the curves which is swinging around goes up to the height of about 5. The second curve goes up to a height of about 2.5. And the third one goes to the height of about 1.2. The curve that moves the lowest has the largest value of omega, that is the fastest variation. So the penetration is small. The effect goes only up to about this height. So L naught can be interpreted as the penetration depth of the effect of the motion of the base plate into the fluid. When L naught is large, that is for a given fluid, omega is small, the plate is moving slowly or the velocity is changing slowly. The frequency is low. Then the depth of penetration is largest. Let's do one more problem. It is concerning the ocean waves and currents. An offshore oil drilling platform is expected to encounter waves of 4-meter height at a frequency of 0.1 hertz and a steady current of 1 meters per second. determine the parameters for the model wave channel where a 1/16th model of the platform can be tested. These are the kind of channels used for testing this. Big plungers produce waves within the ocean of the required frequency and required amplitude and the required height. There is a flow velocity that is also superimposed on this, and the model rig is placed in this channel for doing the study. The governing equation for this flow about an offshore drilling platform would contain the unsteady term and the convective acceleration term because of the steady current, and the term representing pressure forces and gravity forces which play important roles in this situation. The viscous forces are rather unimportant and can be ignored. So the equations would contain these terms: unsteady term, convective acceleration term, the gravity term, and the pressure term. And when we non-dimensionalize this by defining x star is equal to x divided by L naught, a characteristic length, v star is equal to v divided by v naught, a characteristic velocity, t star is equal to t by tau, a characteristic time, or if the frequency is f naught, then we can define t star as f naught t and p star as p divided by p naught. And then this is the equation that results. This number is named after the scientist Vincent Strohl and abbreviated as ST, a very important number that plays an important role in unsteady flow. So, in addition to Euler number and the Froude number, we have Strohl number also that plays a part. Here, the prototype length, characteristic length in the prototype can be taken as 4 meters. The velocity in the prototype is 1 meters per second, the steady current velocity, and the frequency in the prototype is 0.1 hertz. This is the given data. We can introduce a non-gravitational pressure difference script P is equal to P plus rho gz minus P naught, so that terms on the right hand side combine to give only one term, this term. As before, we argue that since there is only one pressure, the atmospheric, there is no other pressure, there is no cavitation, the characteristic pressure difference can be taken to make delta P naught by rho V naught square of order 1. So there is only one pi number that occurs in the equation, that is F naught L naught divided by V naught, this Strohl number. But we need to consider the boundary conditions as well, as we have discussed before. The presence of the free surface or liquid exposed to atmosphere introduces a boundary condition P is equal to P naught at Z is equal to ZF x y. So there is the presence of a free surface, and because of the free surface, Froude number now occurs in the boundary conditions, and that needs to be matched. This is a combination of Froude number and Euler number as discussed before. With delta P naught as 1/2 rho V naught square, the dynamic pressure, this can be recast as P star is equal to twice divided by FR square, Froude number squared, ZF star, and Z star is equal to ZF star. Notice that since there is only one pressure, the Euler number can be made to disappear. And so we are left with only Froude number. Thus, the modeling rule requires Froude number and the Froude number to be identical in the prototype and the model for similarity. Matching of Froude number gives VOP divided by VOM, prototype velocity over model velocity, as under root the length scale of the prototype divided by length scale of the model. And since the length scales are given as 16, so taking the square root, we get 4. So the velocities of the prototype would be 4 times the velocity of the model. The steady current velocity in the model should be only 1/4 of the velocity in the prototype. Stroll number matching gives the frequency for the model to be 0.4 hertz, 4 times that of the prototype. Prototype was oscillating with 0.1 hertz. Since the flow geometries are to be similar in all aspects, the ratio of the height h of waves should be same as that of the characteristic lengths. And so the height of the waves hm is equal to height of the waves in the prototype times the length scale of the model divided by length scale of the prototype. And this gives you 0.25 meters. So instead of 4 meter high waves, we need only a 1/4 meter high waves in the model channel, something that is easy to achieve. Let's do one more example, modeling the spillway of the dams. Water stored in the dams and need to be drained, and when it's drained, since it is a great height, it acquires a lot of velocity. And if the water falls freely, then it will acquire such a velocity that it will damage the surface, the ground below. And so a spillway has to be carefully designed. Typically, this spillway looks like this. The water coming down the spillway accelerates very much, and so this portion has to be designed so that there is a hydraulic jump in which the fluid slows down and the level of water rises in the channel. The spillway of a hydroelectric dam passes a volume of 3 into 10 to the power 6 meter cube per hour and is to be modeled on a 1/10 scale. What should be the volume flow rate in the model test? Since this is a problem with the free surface, cavitation is not important. So Froude number matching is of prime importance in such open channel flows. Reynolds number matching could be relaxed because the dependence on Reynolds number is low, as discussed in the beginning of this lecture. Thus, the modeling rule is simply the matching of Froude number. Froude number for the model should be same as Froude number for the prototype. From this, we get the velocity ratio VOP over VOM is equal to LOP divided by LOM. And the volume flow rate? Volume flow rate should vary like the velocity times the area. And since it is geometrically similar, the area would be like characteristic length squared. So the volume flow rate in the prototype would be V0 L0 squared for the prototype, and for the model, this should be M. And this gives you 10 raised to the power 5 by 2. So given that the volume flow rate of the prototype is 3 million meter cube per hour, we obtain the volume flow rate model should be about 1/100th or little less than 1/100th of the flow rate in the model. Thank you.